Hello, my name is Sungil.
And I'm Jonathan Cabaz.
We worked on designing a PID controller for a self-balancing bicycle. And for the main focus of this, we were looking at the equilibrium of two-wheeled vehicles, mostly because with other autonomous vehicles being four-wheeled, they don't really have to worry about leaning like left or right based off of the off-balance when moving in different directions. But with two-wheeled vehicles, that's a big factor that needs to take into account, otherwise it would topple over on itself. So the objective was to make the system stable with a reasonable settling time and maximum overshoot being the two main factors that we were looking into. We did this through the use of a PID controller to stabilize the system. And for the two-wheeled bicycle, these were the main aspects that we were focusing on. And for the bicycle parameters, we were given, based off of the sources that we used, this list. Some of the main things that we focused on with this were the mass of the bicycle itself. It's split between the flywheel and the bicycle itself. The flywheel being important because that's what drives the bike and pushes it forward. The other important things include like the speed of rotation of the flywheels, so that's how fast that they'll rotate. That's done in radians per second through omega. And one of the major components that we're looking into would be the torque of the system. And for a more real-world application, the maximum torque would be one of the limitations that we'd be looking at, because once it gets past that point, then there's no need for the controller itself to compensate for it. And so for that maximum torque, it is done by multiplying the flywheel angular velocity with the radial momentum of inertia around the cog. And that will give you the maximum torque of the system. And then of course there are other major components being things like gravity, which is just a constant force pointing downwards towards the system. And that would take into effect as well with the forward momentum force pushing it forward, and the left and right forces being pushed when the vehicle itself turns. And these are all taken into account when determining how to stabilize the system and stop it from toppling and falling over. Looking at the PID controller that we decided to use for the system, it was based off of the base PID controller being the KDS squared plus KPS plus KI. And so we have that as our equation 1, along with the closed loop version of it as our equation 2. And then looking at the state space representation of the bicycle, this was supplied by our first and second source. So we kind of used their equations with their variables and ended up with this state space representation.
So here's applying the bicycle parameters. So on MATLAB, we decided to input our state space variables. So we had our A, our B, our C, and our D matrix. We were able to convert that into a transfer function. We noticed that the transfer function actually was not stable. One of the poles, we had a positive value which gave us a negative right at negative 4.065 e to 0.5. So system specifications, the system without controller is unstable, so we need to create a controller to make it stable, so that way we can get a lower overshoot and a settling time that's very small, so that way if someone is riding the bike, they'll immediately be able to self-adjust. So we decided to create the PID controller using MATLAB, and we use PID tuner to make it a lot easier and much more efficient for us. So here's our simulation results using a PID tuner. So we calculated the transfer function, and we basically imported it into PID tuner with that transfer function, and we added the PID controller. That way we can see how our KP, KI, and KD variables are being changed. So we looked into the KP and KI were changed a lot due to what's currently going on and looking into the past and how it's being affected. We came out with a settling time of just under 3 seconds, which would be really fair for what we were looking in for the bike. And our overshoot was only about just under 30%, which with the settling time, I think it wouldn't cause that much of an issue. We had a little bit of oscillation at the input, but since a bike is probably not going to be on a flat surface, there's not going to be that much of an effect in terms of discomfort for the rider. So to conclude our presentation, the system initially started off unstable, and with an application of a PID controller, we were able to make it stable by adjusting KP and KI values. We lowered the settling time below 3 seconds as well, therefore it wouldn't take too long for the system to adjust while there's someone on it, or if it's going to be autonomously driven. And we lowered the maximum overshoot to below 30% because we wouldn't think that cause an issue in terms of how fast that rise time is, and 30% doesn't seem something that would cause an issue.
Here's the list of the citations that we based our paper around.
Any questions? Anyone?
No?
No? Any questions? No? Well, thank you for your time.